I think. So the transmission line is a pair of lines in general to start with, and it carries the electrical energy from source to the destination. So in electrical engineering, they use these transmission lines to transfer the power from the power generating point, maybe a hydel station or a thermal power station, to a consumer point like an industrial load or a domestic load or something else. So there, they'll be worried more on the high voltages and high currents that are flowing, and there they'll be bothered about the breakdown voltages and other aspects. In electronics and communication engineering, we are also equally interested in the aspects of these transmission lines, where we would like to send signals of varying frequencies from one location to another location, which are widely separated. That is, a transmission line is used to transfer voice signals, like in your telephone system, or to transfer video and audio signals, like your TV channels. Like from the dish TV operator to your home, there is a coaxial cable that's running. Similarly, you are getting internet signals from your telephone exchange or similar system to your home through coaxial cables. And many of you must be using a headphone for your music signals from the iPad or mobile or some other similar device. So most of them are also transmission lines carrying the signals from the handheld device to your earphones. So there are several applications we are doing in this manner, and here we are now more concerned regarding the frequency of operation, unlike electrical engineers, where they are more bothered about the power that's flowing in or the high voltages, high currents, etc. And most of the cases, their frequency of operation is around 50 hertz or something close to it. Whereas in our case, we are more bothered about frequency of the signals of 0 hertz, 10, 15, 20, 100, 300 kilohertz, megahertz, even up to gigahertz. So we are now interested to send the power from one location to another location without any change in the shape of the signal. Our concern mostly in these discussions will be on the signal shape, or no distortion is to be added, and how we can design the transmission lines for this aspect is our main concern in these discussions. So to be able to understand the operations much better, we convert the physical parameters of the transmission line into electrical equivalent parameters and try to develop a equivalent circuit for the transmission line, so that we can apply our KVL, KCL, etc. to understand the voltage and current behavior. So in all these transmission lines, we are now going to take one more additional feature or the concept here as the transmission line effect, or propagation delay is going to be the major concern in all these discussions. What is that? That is, as the signal travels certain distance, say L, with a velocity v, it will give rise to a time delay of L by V. That means from the input to the output of a circuit, if when the signal travels, the traveling time is taken as the length of the system or the network or the component by the velocity. Normally we take this velocity as 3 into 10 power 8 meters per second. So as the lengths we are concerned are about centimeters or tens of centimeters, the time is negligible here. But when it comes to very, very high frequency signals, as I mentioned some time ago, that we are talking even hundreds of megahertz or even gigahertz, the time of travel and the time period of the signal are comparable. That is, the time period of the signal comes down to fractions of microseconds or even nanoseconds for these high frequency signals of hundreds of megahertz or even gigahertz. And the time of travel is again similar to the earlier cases of L by V. So it comes to again fractions of microseconds or nanoseconds. That means there will be one time period of travel for these signals. from input to the output. That means the signals undergo 360 degrees of phase as they travel from the input to the output of the system or a network or the circuit component or whatever, if the time of travel and the time period of the signal that is traveling are comparable. Or in other words, we say the distance of travel and the wavelength of operation, if they are comparable. The distance of travel we are taking is, say, several centimeters or tens of centimeters in certain cases. So if the wavelength of operation is hundreds of megahertz or close to that, gigahertz or whatever, then the wavelength of operation is also in centimeters or tens of centimeters. That means if the signal travels by a lambda distance or a wavelength of distance, we know that it has to undergo 360 degrees of phase. So if the wavelength of operation is 10 centimeters, then like 3 gigahertz we are talking of. Then from input to output, if the system length is also 10 centimeters, it undergoes 360 degrees of phase. Suppose it is only, say, 5 centimeters distance from the input to the output, then it undergoes even 180 degrees of phase shift. That means as the signal travels through the networks, components, systems and other things, it also undergoes phase shift in terms of voltage and current. So far, this aspect has not been considered. We are now considering this aspect also. That is, distance-wise, there will be phase change. Time-wise, there will be phase change. So both these things together, we are going to take it up. That is the speciality of this subject of transmission lines. That means our voltage and current are no longer simply functions of time, as we have been discussing so far. Now they are functions of voltage is a function of time as well as distance. For time wise, you might have seen that we put it as e power j omega t. That omega is the radian frequency or the time to phase conversion factor, because e power j should always be with phase for the voltage and current. So the omega converts the time parameter into phase. Similarly, we are going to take up another one in this context, that is omega t minus beta z. We are going to put that beta is the parameter which converts the distance to phase. Distance to phase, how is it? Yes, if a wave travels a distance of one wavelength, it undergoes a phase shift of 2 pi radians. So lambda distance is for 2 pi radians. So how much is the distance, whatever we are talking of like z, how much is the phase it is to undergo? We take it as 2 pi by lambda. So 2 pi by lambda times z will be the phase the signal undergoes as it travels. So this 2 pi by lambda factor is what we are going to put it as phase constant or simply phase shift constant, which has the units of radians per meter. Okay, so earlier also you have omega, which is having the units of radians per second. So as it is going to convert time to the phase, so it should be radians per second. Now new term which we are introducing, beta, is to convert distance to phase. That's why it is radians per meter. Okay, so let's go to the details of these aspects more and more now. So as I told you earlier, that we are now going to convert the physical parameters of the transmission line into equivalent electrical parameters. They are known as primary constants. So let's talk about these primary constants and take what are the aspects of these things and work out more and more on these details. Okay, so this is what we are going to study. As I've shown you earlier, this is one type of transmission line which we normally call it as coaxial cable. So this outside copper is one conductor, the inside copper wire is another conductor, and in between these two things, to protect the signal not to get shorted, we keep a insulator. So this dielectric to protect the entire system, the outside conductor, insulator, and the inside one, to protect them together, we keep a plastic sheath or a plastic cover of all these things. So A is outer plastic sheath, B is first level copper conductor. So to have flexibility, we don't put a full conductor here. We put several wires and put it into the form of a grid. All right, very closely knit wires together. That's what we call as copper screen. So copper screen is there. That is B. Then C is your insulator, dielectric material to protect short circuit between inner and outer conductors. The D is the inner copper cylinder, which is having a very small diameter. So this is the one, the D is the one which carries the actual phase of the signal, and B is going to carry the neutral point in general. Okay, so this is what we have been practicing for a very long time. But please mind you, the recent times you are using many adapters or the chargers for your mobiles and tabs and etc. Some of these are coming with the other way. That is, B is becoming the signal and D is becoming the neutral. That's for a simple case which you have to be aware of. As electronics persons, you are using all these sort of adapters. Okay, adapters also come out with connectors and other things you must have seen. So that's a special case. But in general, B, the outer conductor, is connected to the ground, and the inner conductor, that is D, is connected to the signal in general. That's the standard factor. Why do we call it as a cable? A pair of wires, if you are putting together in one conduit, that is in a plastic rubber pipe, when you are carrying it, we call it as a cable. But here, they are not separated, they are one inside the other. The two conductors we are talking of, the B and D, are one inside the other and having the same axis of these two cylinders. Thereby, we call it as coaxial cable. Okay, cable means the one which is carrying pair of conductors. It can be only one pair or several pairs. That's what you might have also observed. The telephone people from your locality saying that a cable is going from here to the telephone exchange. That means in your locality, if there are 20 phones, say, so 20 pairs of wires will be brought together to a common point, and all these 20 pairs are taken to the telephone exchange through one single hollow pipe. So that pipe is known as the cable. Okay, so that's how we should be more careful with these things. So this is the structure what we have in mind, an open wire transmission line. What you see is the telephone cable running parallel to the road. You might have seen that is the one which we have in mind for our discussions here. So A is the radius of the wire, D is the separation between the two centers of the wires, and the medium between these two things has the parameters mu, epsilon, and sigma. Okay, mu is the permeability, which is given in Henry's per meter. Epsilon is permittivity, given in farads per meter, and sigma is conductivity, given in Mohs per meter or Siemens per meter. Okay, so the lines can also be something like this, called a planar line. The top and bottom conductors carry the power, and in between these two things is a rectangular dielectric sheet. So this is one variety, planar lines. Okay, this is a strip line. Like top and bottom side, you will have two conductors, and in between the dielectric there is one more metallic conductor running, which is carrying the line. So this is a 3 conductor system which will carry the power within that all the time. So it is known as a strip line, because all these 3 conductors are flat copper strips. So, and in between these two things, these things, there is a dielectric material here. So strip line is very much used in most of the telephone circuits at high frequencies to have a very good response functions. Yeah, this is the one which we are going to start with for our discussions. As I told you some time ago, the voltage and the current along the line will have some change from input to the output of the transmission line. So we are taking a very small length of line, say delta Z length of line. So the current is I at the input, whereas I plus delta I at the output. The delta I is the change that happens due to the distance as well as time. Okay, so V is similarly the voltage at the input, and at the output side V plus delta V is the voltage that's going to be there. That plus delta V is for just easy understanding and starting point, but actually the voltage is going to be less for various reasons. Similarly, the current output is also going to be less than the input. So technically speaking, it can be even I minus delta I. That's what you might see in some of the standard textbooks. So I minus delta I, V minus delta V is also equally valid. Okay. Now, what happens when you apply a signal at the input side of this transmission line, a pair of lines? There will be electric field lines between the two conductors. That's what is indicated as yellow lines here. And the electric field is the dou V by dou X. Okay, minus dou V by dou X. So electric field can be obtained, which we expect it to be perpendicular lines to the normal transmission lines. Okay, and similarly, there will be magnetic field loops, not lines, because we know magnetic field lines are always closed loops. So magnetic field loops will be there around the conductors, and depending on the current direction, the field loops will have the direction of flow. Okay, some will be clockwise and the other side will be anti-clockwise. Okay, one side of the conductor there will be clockwise, and the other side of the other conductor there will be anti-clockwise. Why? We know there is a standard rule by which we have to identify the direction. Okay, so right hand rule is there with us. So this is about the electric and magnetic fields that are going to exist due to the presence of voltage and current on the line. Okay, so what happens with these things? There will be a potential difference, as we know, and electric field lines are established. Similarly, magnetic field lines are also established due to the current and other things. So how do we write an equivalent circuit for these things? As we know, the current is changing across the lines. So putting these two things together, we take it that the current change is due to the resistance offered by the wire. Why does the wire offer a resistance? Because the wire is having some finite conductivity and finite size in terms of length and area, surface area. So rho L by A type of thing is going to work out. So as the resistance that is offered is dependent on the length, rho L by A, rho is the conductivity, L is the length, and A is the cross-sectional area. So we would like to take it per unit length how much it is. That will be easy for our calculations, so that our calculations are valid for any length of the cables that are going to be there. So we are now going to introduce a new set of parameters called per unit length parameters. Okay, so R by L is what we are going to take up, which is same as rho by A. So this R by L is also loosely called as resistance offered by the transmission line, but it should have been exactly known as resistance per unit length. Okay, ohms per meter, right? So there will be some resistance offered by the line, and due to the current flowing, as we know, there is a magnetic field surrounding it, so there will be a back EMF created on this. So taking all these aspects, we would like to introduce a inductance parameter, that is magnetic flux linkage per unit current. Okay, that is going to be taken up. So L is also going to be introduced, as these two things appear due to the wire carrying the current. So R and L parameters are put in the series form of these things. Okay, so in series they are going to appear, and this R is not purely resistance, it is resistance per unit length. So the net resistance over a distance of delta Z is going to be R into delta Z. Similarly, the net inductance offered is L into delta Z. So L has the units of henries per meter, R has the units of ohms per meter. So over a length of delta Z, these are the two things which are going to be there as equivalent circuit parameters of this line. Similarly, between the two conductors, there is a medium. So the medium has parameters like mu, epsilon, and sigma. That's what we have accepted earlier. So due to a small amount of conductivity that is present, when the current is trying to flow from one side of the input to the other side through the transmission line, there will be a small amount of leakage that can happen. Okay, the leakage may be very, very small, but still we have to account for it. So to account for the leakage flowing from one side of the line to the other side, then this G into delta Z is introduced. So as it appears between the two conductors, we are putting it as a shunt element. So again, conductance, though we say it is exactly conductance per unit length, so it is moles per meter. Or a length of delta Z, it is G into delta Z. So between the two conductors, as there are electric field lines, due to the voltage applied, there will be a small amount of capacitance that also gets developed. So this capacitance is again introduced into the equivalent circuit as a parallel element. And though we say capacitance again, it is actually capacitance per unit length, farads per meter. And over a distance of delta Z, the net capacitance offered is C into delta Z. So over a delta Z length, we have 4 parameters for the transmission line to represent in its equivalent circuit. What are they? R, L, G, and C. R, L, G, and C. Please remember, loosely we say RLGC. As per actual English, it should be RLG and C. And please remember, in the interview process, sometimes we try to confuse you, say that R is resistance and G is conductance. Why not R is equal to 1 by G or G is equal to 1 by R? Please be aware that R is due to the resistance of the line and G is due to the conductance of the medium between the two lines. R is due to the line conductance parameter, that is copper, aluminum. As you change, R value is going to change. And the medium is independent. Medium can be air or something else. So the medium conductance will be taken as G. So they are independent. G is not equal to 1 by R. Okay, R and G are independent things. That is what the most important aspect one has to remember in this. Now, RLGC are dependent on the physical parameters of these transmission line structures. That is, what is the material used for the wires, what is the spacing between the conductors, what is the medium between the two conductors. So these aspects, and what is the structure of this transmission line? Is it cylindrical, square, or rectangular? What type of wire is being used? So that makes the L values. Okay, so R, L, G, and C are the electrical parameters which are dependent on the physical structure and physical characteristics of the actual transmission structure. So various types of transmission lines, whatever we have, we are trying to bring them into one type of analysis by converting the physical structure into these electrical parameters. That's the important. Everything is brought into this particular stream of RL, G, and C. Once we have RL, G, and C of a structure, the analysis is same for all the types of structures. That's the advantage with these RL, G, and C. Okay, same analysis we can do for any type of structure. Okay, so RL, G, C are known as primary constants. Why are they called primary constants? They are the first electrical parameters of the physical structure, because we want to operate this in an electrical domain with applying voltage, current, power, etc., and see what is happening, what are the ways and means to change its performance. We are trying to understand. So whatever is happening in the physical domain, like two wires are there, some spacing is there, wires are having a circular cross-sectional area of this much, the conductivity of material is this much, all these are all some domain. What is the first job of an engineer is convert all these domain specific parameters into your domain equivalent convenient parameters. This is what an analysis person must do first. That's what the logic one has to remember in this. Whatever be the physical parameters, what is happening and other things, everything you bring down to a first level, your domain interested parameters. How to convert them is the most important job. Then once we get R, L, G, and C, then once we have this equivalent network, then we can apply our KVL, KCL, etc. and try to find out more interesting informations from these things. Okay, so here we have the equivalent circuit in this format, and in this equivalent circuit, now in this equivalent circuit, the input current is taken as I z comma t, and the output current is I z plus delta z comma t. At the same time, what is happening, we are trying to take. So all are in terms of same t value. That's what one has to remember. Okay. So similarly, the input voltage is V z comma t, and the output voltage is V z plus delta z comma t. That means at the same time, what is happening with the distance is being observed. So all our calculations and our things are valid instantaneously. At the same time, what is happening is being understood. So when we apply KVL to the first case of your series arm, then you have V of Z of t. V of Z of t is whatever is the current flowing through this R I Z of t plus L delta Z I Z of t, okay, plus whatever is the voltage between these two things. That is V Z plus delta Z comma t. That's how the loop is getting completed. Similarly, whatever is the current, we have this current equation at this node, we are going to take it up. For this, whatever is the circuit parameters, we are going to talk about. So from KVL, V Z of t, that is for the series elements, R delta Z is the series resistance times the current plus L delta Z is the inductance, and the net voltage is rate of change of current. So dou I by dou t of this plus the voltage available on the other side is V of Z plus delta Z comma t. So this is the first equation what we are going to write for this. Then this V of Z of t and V of Z plus delta Z comma t are taken together, and all of other things are brought to the other side of the equation. So this is minus of, that means this has been taken to the left side and put as the first one. So V of Z plus delta Z comma t minus V Z of t by delta Z, that means delta Z is here, delta Z is here, is brought down onto the left side. So what is left on the right hand side? R I Z comma t plus L dou I by dou t, basically. So Ri plus del dou I. So this V Z plus delta Z minus V of Z by delta Z as is represented as dou V by dou Z. Okay, when delta Z becomes limiting case of 0, then it can be written as dou V. Why dou V? Why not dV? Because we are considering that the time and distance variables are independent. So we are now taking only the distance wise differential. So the time wise it is independent to that. That's what is the understanding. That's why it is not a full differential, it is a partial differential. So partial differentials are more convenient to handle compared to full differentials. So we try to orthogonalize the problems. That means the distance variations and time variations, we are taking them to be independent. Right? So that is the equation what we have. So whatever is there in this, you can see on the left hand side you have voltage, and on the right hand side you have the current. So the voltage and current are related to this. Two unknowns are there, only one equation is there. Not sufficient for us to solve. So we go for identifying another equation, that is from KCL. So now we apply the KCL at the center, that means at the node point. At this point we apply the KCL. So one current is I of Z of t is coming out, I of Z plus delta Z comma t is going out, and one more current is going in this manner into the shunt arm. So taking these three things together, we can formulate the KCL. So I Z of t is the input, or the coming in towards the node, and whatever is going out from one side towards the output is I Z plus delta Z comma t, and whatever is going towards the shunt arm is G delta Z times V times Z plus delta Z comma t plus C times delta Z. C delta Z is the net capacitance multiplied by the dou V by dou t is the current that's flowing in the capacitor. Okay, so this is the way we try to find out these ones. So the current is dou V by dou t into this. The current is proportional to the V in this, okay, because it's a conductance arm, whereas this is a capacitance. So this is again taken to get your differential with distance, okay, because the time is again orthogonal to the or independent of the distance variation. So dou I by dou Z, again we are going to have is equal to G times V of Z comma t plus this, okay, C delta V by dou t. Is it correct? What is a small change we are making in this, right? Is it correct? Here, whether this V is Z plus delta Z, but here we are writing that it is almost equal to Z comma t. That's how we are making a small error into this. So this error will be very small as long as delta Z is very close to 0. For small sections of the transmission line, this can be the approximation. Okay, so thereby this is, that means the voltage across the equivalent circuit is considered to be same when the current is considered. When the current is considered, the voltage across this is considered to be same. Okay, so that's what the case is. And similarly, current is considered same when voltage is the equation what we are going to consider for this. Okay, so that is how we are going to modify this, because this is an unsymmetric network, is it not? So this unsymmetric network cannot represent a symmetric transmission line as it is, because our transmission line can be used in either ways. Bilaterally it can send the signals from left to right or right to left. Whatever way you send the signals, they will undergo the same amount of changes. So we try to put R delta Z and L delta Z as two half parts, R delta Z by 2, L delta Z by 2 on the left hand side of this parallel arm, R delta Z by 2 on the right hand side of the parallel arm we are going to put. Then the currents will get disturbed. So in such a case, we take the current to be same when voltage equations are being formed. When current equations are formed, we take the voltage to be same. This is the approximation what we need to do. That means how efficiently we try to put these things is another important aspect. How to simplify the things, one must be aware of this. Okay, so this is an unsymmetric network which is not appropriately representing. That's one thing one has to remember. The other aspect one has to remember in this is where is this R located on the transmission line? Where is the L located? Where is the G? Where is the C? If you want to identify, they are all distributed along the entire length of delta Z. It is not located at one single location, either R or L or G or C. They are all distributed, not located at one location. That is, they are not lumped elements. They are distributed elements. R, L, G and C are distributed over the entire length of delta Z. So these are known as distributed parameters. In your normal electrical circuits, what you might have seen like R, L, C and other things, you will be placing them in the circuit at one location. So they're all lumped things, lumped elements. Now what we are going to discuss are distributed elements, and accordingly whatever R, L, G and values, whatever we are going to get, they're all distributed values. All along the length of that transmission line, they are distributed. So now what is important here is applying KVL, we have got this equation 3. Applying KCL, we have got this equation 4. Can we solve them? Yes. There are two unknowns, voltage and current, and there are two equations with us. And what is known in this? R, L, G and C are all known to us in this. So if we know the primary constants, we can find the voltage and current variations on this transmission line. But solving two simultaneous equations which are involved with so many terms is difficult. So we would like to have only one equation with one unknown. Can we do some mathematical jugglery in this and try to get one equation with one unknown? That means one equation, if you want, from 3, there are two unknowns, voltage and current. Either you remove voltage into this or current into this and get another one. So we try to get this because dou I by dou t is there in this. So dou I by dou z is in this. But here there is I directly, right? So to be able to get dou I by dou z in this as well as into this also, we try to differentiate this with dou z. Dou z on both sides. When you do, then you have this and this, where you can substitute these aspects into this and try to simplify. That's what we are going to do now. And to start with that, we take some simplification further. That is, the voltage and current are functions of Z, that is along the length of the transmission line, are also functions of time. The time variation is simply taken as e power plus j omega t for all these calculations. Okay, so when we try to simplify that time variations as e power j omega t, our differentials become very comfortable. As we observe in the equations 3 and 4, there are differentials with time. So those differentials we would like to simplify as simply j omega times the same variable. So putting those time variable differentials as j omega, the earlier two equations 3 and 4 will become as simply minus dv by dz is equal to r plus j omega L times I. Earlier we were using partial and now we are using full. What is the meaning? Now these v's are only functions of z, because already time variation is already taken out. So when we have only one variable, the differential is either partial or full, means the same. That's why this is given as minus dv by dz is r plus j omega L times I, and minus di by dz is g plus j omega c times v. So v and I are there in both the equations. Okay, we would like to simplify this as one equation with one unknown. So how do we do it? By this is I here, whereas what I have in the second equation is di by dz. So to get di by dz in this equation also, we try to take the differential on both sides with the dz. So when we take the differential on both sides with dz, so d square v to dz square is some gamma square times v. Luckily, when we take the differential for the second equation also, we get the same constant gamma square into I. So one equation with an unknown we are going to get. Luckily, we need not solve both equations to get both V voltage and current. If we solve for one equation, you can write the expression for the other one, because the two equations are of the same form. That's the most advantage point. So instead of solving two equations with two unknowns, by this simple trick, we are solving only one equation, solving and getting what is voltage expression. And because the original equation is the same form, the current expression also follows on the same lines. So one equation, if you solve, it is sufficient to get it. That's what the advantage we want to derive by going for this second differential. But what is the penalty on this? The penalty is that instead of first differentials in the equations given above, dv by dz is only related to I, di by dz is related to v. First order differentials are used, but two equations we had to solve. Here we have second order differentials, okay, but one equation with one unknown. But now luckily we have second order differential equations can be solved very easily using your sine function, cos function, exponentials and this sort of things. So we take help of that in the analysis aspect. So now what is gamma in this? Whatever has been introduced, the gamma is given as square root of r plus j omega times g plus j omega c. And as we are taking a square root, normally we take the gamma to be with a plus sign only. That's only convention. Okay. So r plus j omega l is there in the square root. G plus j omega c is also there in the square root. So gamma is going to be definitely a complex quantity. This complex quantity we are trying to represent as alpha plus j beta. Alpha is the real part, which we call as the attenuation constant, and beta is the phase constant, the imaginary part. And alpha attenuation, why does it represent attenuation? How much reduction in the amplitude is going to take place as the voltage travels along the transmission line of distance z, or the current travels, how much reduction in the current is going to happen is represented through this alpha. So this alpha has no units basically because it is a ratio, but what we normally represent this as a Nepers per meter. Okay, what is Nepers and other things we shall see later. Similarly, the imaginary part is representing what is the phase change that's going to happen for the signal as it travels. So this phase beta is known as phase constant or phase shift constant, and it is having the units of radians per meter. So gamma is a peculiar thing. Real part represents the change in the amplitude. The imaginary part represents the change in the phase with the distance. So what are the units of this quantity, gamma? One is having amplitude variations given in terms of Nepers per meter. The imaginary part is given as phase changes with phase with having units of radians per meter. So finally gamma is having the units per meter. Please remember, most of the interviews people ask what are the units of gamma only, because everybody can easily answer alpha and beta. They will not be so strong with the units of gamma, which is not mentioned in most of the textbooks. That's why we have put it exclusively here as per meter. That's it. Okay. So this gamma is truly representing the behavior of the wave as it travels along the transmission line. Because amplitude changes will occur, phase changes will occur, no change in the frequency. As the signal travels through the transmission line, the one characteristic that doesn't change for the signal is the frequency. So the amplitude variation is represented through alpha, the phase variation is represented through beta. That's why the two symbols are taken in very easy form like that. Okay, so propagation constant is an important term which we all need to remember for all these discussions. So the name is apt because as the signal travels or the propagates through the transmission line, what changes will occur per unit distance. Okay, in terms of amplitude and in terms of phase is truly represented by this parameter gamma. So gamma is thereby known as propagation constant. Okay. Now, so gamma is known to us with the alpha and beta. Okay, how do we know alpha and beta? Because we already know R, L, G and C of the transmission line, and we also know the frequency of operation of the signal. So radian frequency we need to know. So taking these two things together, your propagation constant is decided. So propagation constant is also known as a secondary constant, because primary constants are RLGC. Knowing RLGC and the signal frequency, We are coming to a second level of important parameter which represents the changes directly. So this gamma is known as secondary constant. Okay, and in terms of these things, now we are going to represent the voltage and current along the transmission line. So the voltage has to have two components, V plus and V minus, because both of them will satisfy the basic equation. Dou square V2 dou Z square is equal to gamma square V can be satisfied by e power plus gamma Z as well as e power minus gamma Z. Okay, so for e power minus gamma Z, we take the amplitude of that function variation as V naught plus, and e power plus gamma Z, we take the amplitude part as V naught minus. Why we are choosing like this? E power minus gamma Z, we have the convention that this represents the voltage wave traveling in the plus Z direction towards left to right. From left to right, whatever is the travel, we try to represent as e power minus gamma Z. So at Z equal to 0, whatever is the amplitude, that is the highest value. That's why it is V naught plus. It is given. So this is the way. Similarly, e power plus gamma Z represents the voltage wave traveling in the minus Z direction. Traveling in the minus Z direction, and whatever is the amplitude of this wave at Z equal to 0 is what we call as V naught minus. So V naught minus is for the wave traveling from right to left or in the reverse direction. E naught minus gamma Z, e to the power of minus gamma Z represents the wave traveling towards the positive Z axis with an amplitude starting as V naught plus. So V naught plus is the starting point, and as it progresses, its value goes down and down. How? By the real part of the gamma, that is alpha decides how much is the reduction that's going to take place with the distance. Okay, and similarly V naught minus is for the starting point, and as it progresses towards the minus Z direction, whatever changes are going to happen, that will be again represented by your gamma real part alpha. Okay, so this is one thing what we are going to see, but by looking at the voltage expression and the original equation that governs the voltage, we can see that even the current also follows the same lines. So the current expression is directly written, okay, without going through any of the analysis methods required, because the equation is of the same form. Instead of V, you just write I. So I of Z is equal to I plus of Z plus I minus of Z. That means it, again, two types of waves can satisfy the differential equation whatever we have. Second differential must be equal to the original function. That's the only way. D square I is the second differential. So that must be equal to some constant times I. That is sufficient for us. So second differential, again coming out to the same thing, is satisfied by your exponential functions minus gamma Z and e power plus gamma Z. So we take that actual solution as a combination of these two waves, e power minus gamma Z and e power plus gamma Z. Now, for e power minus gamma Z, we take the amplitude part as I naught plus, and for e power plus gamma Z, we take the component as this. Okay, so this is what we have at this time, and now going into the details, voltage and current, we are able to get it. Is there any problem? At some location, I think. I'm not able to see. Okay, yeah. So voltage is varying with distance, current is varying with the distance. How? Like some exponential functions. This is the new thing which we call as the transmission line effect. Please remember, most of the interviews people ask you, what is a transmission line effect? Transmission line effect means in the normal regular electrical circuits, we take the voltage and current at the input and output to be of the same phase. But here it is not. Okay? To the normal simple circuits like resistors and other things, whenever they are used, we take the input and output to be of the at the same phase with reference to the distance. But here it is not. Why does it happen? Because of high frequency signals traveling through these networks or transmission lines or circuits. So the lengths are proportional to wavelength of operation. L by lambda is close to 1. Okay, maybe 0.25 or 0.5 or 0.6, 0.31, 0.29, something like this. Accordingly, there is a phase change between input and output, even though the line is simple transmission line. So that is the one which we are discussing more seriously now. So I and we have got the expressions so far, and these expressions will be changing depending on the type of line. How? Through R, L, G and C, because for different structures, R, L, G and C are going to be of different values, and once they are changed, you know that the R gamma is going to be definitely changed. One more thing that can also change gamma is your omega, that is radian frequency of operation. If the input signal frequency changes, then also the gamma value gets modified, not only with the transmission line, but also with the frequency of the signal traveling through the transmission line, the propagation constant gets changed. And this is having real and imaginary parts, alpha and beta. The real part is about the amplitude variation, and the imaginary part is about the phase variation we are talking about. Why only amplitude and phase? Because the third important parameter of a wave, that's the frequency, it doesn't change from input to the output. So we are not bothered about it at this time. Okay. So this is about the case of your so now let's try to understand things somewhat better with reference to the variations and other things. Okay, so here we have now an important parameter coming up, which is again a very standard interview question. Okay, what is this standard interview question is? What is the impedance of these lines? Okay, what is the characteristic impedance of this? So before we go into it, we'll try to take for the earlier equation of voltage variation along the transmission line, whatever expression we have got for the voltage, we are going to substitute. So dV by dz minus is equal to R plus j omega L times I is now substituted with whatever is the voltage expression we have got in terms of forward and reverse traveling waves of voltage as well as current. Okay, so this is coming out as the V naught plus by I naught plus is equal to R plus j omega L by I by gamma. How? That is, here we take the differentials, right? So V naught plus e power minus gamma z and minus goes off, and V naught e power plus gamma z is plus gamma. So that gamma is the common one in this, and similarly here the same thing is there. Okay, so if we take the real part, that is when the line is having V naught plus and I naught plus ratio is one thing, because you have R plus j omega L by gamma per it, and V naught minus and I naught minus with a minus sign, it is also same as R plus j omega L by gamma. So when there is no reflected wave, what is happening? Okay, if the line length is very, very long, the reflected wave is not going to be there. So here we have V of z simply given as V naught e power minus gamma z, the one which is traveling from the source towards the end of the line, which is at infinity point. Similarly, current is also having only one component, that is I naught plus e power minus gamma z. Under such a case, If you take the voltage to current ratio, that is known as the characteristic impedance Z0. Okay, characteristic impedance is for the semi-infinite long line. Okay, whatever is the voltage to current ratio at the input, that is known as the characteristic impedance. This word is going to come quite often to us. Okay, so every line, whenever we are using transmission line, depending on the voltage and current distribution on that, there is going to be a characteristic impedance for that. So how this characteristic impedance is going to be calculated, you can see here, that is input impedance of a very long length of the transmission line. If you take input impedance, means voltage to current ratio at the starting point. But what is the condition? There should not be any reflected waves. Under that means, under that condition, whatever is the voltage to current ratio, that is known as the characteristic impedance of the line. That means it is acting like an impedance of so much for all the sources. Okay, or for the load, if you are connecting, it acts like having an output impedance of this value. Okay, so this is a very important aspect which comes to us quite often in all our future discussions. Why the name is given as characteristic impedance? Because it is a specific value of the transmission line under consideration. How this is decided? This is decided based on R, L, G and C, okay, and also the frequency of operation. Okay, and thereby for different frequencies, you have again different characteristic impedance values that are possible. So once we say impedance, ideally you may have either complex value, but most of the cases we try to get it as only a simple real number. Okay, but as long as you have this characteristic impedance given as voltage to current ratio, obviously it has the units of ohms. Okay, characteristic impedance. That means it is a specific value of the transmission line. Like every student, whoever is studying in the college, we say is attached with a percentage number. Like a student has 76%, or another student has some 83%. We say they're all very bright students by knowing the number itself. The academic performance is indicated with a simple number like a percentage. Similarly, here the impedance level with which the signals will be traveling through the transmission line will be indicated through this value of V to I ratio. Thereby, this is having the name as characteristic impedance. Earlier days, we used to call it as eigenimpedance. Eigen is a German word indicating characteristic, very special number for the individual transmission line. That's why eigenimpedance is one name. Your friends in electrical engineering, they talk of this as driving point impedance, right? Sending end impedance, like this also they talk of. But in electronics and communication engineering, we say this as only characteristic impedance. So this has the units of ohms. Okay, so this is something on the importance of this characteristic impedance. It is defined as the voltage to current ratio of a infinitely long transmission line. Okay, so what is the expression by which we can calculate this? So R plus j omega L by gamma is also equal to gamma by G plus j omega C, and if you substitute what is gamma, it is root of R plus j omega L into G plus j omega C. If you take, then the Z0 is a ratio of the R plus j omega L to G plus j omega C under square root. Okay, that means R plus j omega L, what does it sound? It sounds the series net impedance of your electrical circuit. What about G plus j omega C? The net admittance of the shunt element of the equivalent circuit. So Z0 is another standard parameter which can be used for all our calculations of the transmission lines. Thereby, the Z0 is also another secondary constant of the transmission line. So, what are the primary constants? We know already. R, L, G and C are the primary constants. Using them along with the frequency of operation, we put another set of parameters, only two, that is gamma and Z naught. They are known as secondary constants of the transmission line. In this, the gamma is a function of the distance, whereas Z naught is simply a constant. So it has the units of ohms. It is not dependent on length, because already we mentioned in the definition itself that the voltage to current ratio of a infinitely long transmission line is characteristic impedance of that line. Okay, so this is a very important parameter with which we can work out and find out whether the line is working okay or not so okay, or what are the things we need to do on these things. Okay, so the actual engineering operations of transmission lines will be based on Z0 and gamma values. Okay, that is the importance attached with these two things in this. Okay, so now let us try to see one or two simple problems on these aspects, and see this problem first. Are you able to observe this? Are you able to observe the problem? Right? Are you able to see this problem? Say yes like this. Okay, so this is the one which we are going to work out step by step now. So let's try to make it as a big one like this. So in a lossless transmission line, the velocity of propagation is 2.5 into 10 power 8. Capacitance of the line is 30 picofarads per meter, and find the other parameters of interest. Oh, this is already not mentioned to us. Okay, 1 minute. The other problem is better. Other problem is better, right? 1 minute. Yes, this is the one. Please, at a frequency of 4 megahertz, a parallel wire transmission line has the following parameters: R, L, G, and C. R is 0.025 ohms per meter, L is 2 microhenries per meter, G is 0, C is 5.56 picofarads per meter. Most of the cases what we handle in our day-to-day activities, the G is generally very, very small. If in any particular problem G is not mentioned, you can safely take it as 0. Okay, the line length is 100 meters, terminated in a resistance of 300 ohms. Okay, so that's what other parts will not bother. Let us try to talk about what is the characteristic impedance of this particular line. What is the given data? The data is F is 4 into 10 power 6 hertz, that is 4 megahertz. R is 0.025 ohms per meter. L is 2 into 10 power minus 6 henries per meter. Z is 0. C is 5.56 into 10 power minus 12 farads per meter, and the length of the line is 100 meters. Okay, so what is omega here? So the omega is 2 pi f, 2 pi into 4 into 10 power 6. So that is what one has to calculate, and then find out the Z naught. The Z naught is taken as square root of R plus J omega L by G plus J omega C. So when you substitute the given values of R, L, G, and C, and whatever we have calculated as omega, if you introduce into this, you should get the characteristic impedance as 600 minus J 0.149 ohms. 600 minus J 0.149 ohms, you must be able to get from this. Okay, so this is the first problem what we can consider for our easy understanding. Okay, R, L, G, and C are given. Frequency of operation is given. So with the given frequency of operation, we have calculated what is omega, and then substituted these values into our equation for the characteristic impedance. Square root of R plus J omega L by G plus J omega C. So when you take the R plus J omega L into amplitude and phase form. G plus j omega c, again amplitude and phase form. Amplitude ratios you can calculate and phase differences you can calculate. Then square root of the amplitude ratios will give you the final amplitude of the Z naught, and half of the difference between the two phases gives you the phase of the characteristic impedance, and from the amplitude and phase components you can put again real and imaginary parts. So the real and imaginary parts of the Z naught will be 600 minus J 0.149 ohms. You may check it up later and get satisfied with the results whatever we have got. Okay, so this is the way we can find out the actual very useful electrical parameter of interest from the RL, G and C. How to get RL, G and C is again a simple calculation where R is worked out from rho L by A and G is calculated from the medium characteristic, whereas L is calculated from the shape of the conductor and knowing how much magnetic flux linkage is going to be there for such a case from the two lines. Okay, so the magnetic flux linkage per unit current is your inductance. How about the capacitance? Between the two conductors, depending on the structure, how the electric field lines are going to be there, we try to find out, and from that how to calculate the voltage difference and how much charge is going to be there. So charge per unit voltage we try to calculate, and that gives you the capacitance offered. So these are the ways we try to first find the RLGC primary constants, and from them the secondary constants Z0 and gamma will be calculated. So in this case, as we have already R plus j omega L as well as G plus j omega C, you can also calculate what is the gamma of this, okay, and find out the real and imaginary components. Square root of R plus j omega L into G plus j omega C, if you calculate and find out the real and imaginary components, they give you alpha and beta values. Okay, so this is on the first simple case of calculating the okay. Now let us consider the simple case of a lossless line. This is what also you must have seen the other problem. Okay, a lossless line is represented in the parameters as R equal to 0 and G equal to 0. There is no radiation or other type of loss, ohmic loss on the conductor carrying the signal. So that is R equal to 0, and there is no leakage between the two conductors, that is the dielectric medium. So that is G equal to 0. So what happens with the gamma? Gamma is square root of R plus j omega L into G plus j omega C. When R and G are zeros, then it is simply two imaginary components product square root. So again you are going to get j omega root LC. So j omega root LC is the value of gamma, indicates that the real part is 0. The real part is alpha. So alpha is equal to 0 and beta is going to be omega root LC. This is a very favorable condition what we want. That means as the signal travels through the transmission line, there is no change in the amplitude part of it for the voltage or the current. There is only phase shift for the voltage and current. The phase shift is decided based on the frequency of operation or the omega value and the L and C of the transmission line under consideration. So omega root LC indicates that with the frequency of the signal, the phase shift is proportional to it. The phase shift is linear relationship with the frequency of the signal. That is a very favorable situation where if you find what is the velocity of the signal that is traveling along the transmission line, as we have calculated earlier, that the velocity is omega by beta. Velocity is defined as omega by beta for these things. So Omega by beta in this case is going to be simply a constant, 1 by root LC. Okay, so the L and C values decide the velocity with which the signal is going to travel on the transmission line. So though we expect it to be the speed of light 3 to 10 power 8 meters per second, but on the transmission line the L and C values also will have a play on these things. Please remember, it is a phase velocity what we are talking about. The actual group velocity will be slightly different in case the line is a different type of line. Okay, and this is 1 by root LC beta alpha. These are all the ones which will be most useful for our networks as well as for long distance wired communications. Okay, nowadays we see very long distance, like hundreds of kilometers or even thousands of kilometers, coaxial cables are laid to transfer the telephone signals. Please remember, under the seas also there are coaxial cables from one continent to another continent covering thousands of kilometers. So for such cases, alpha equal to 0 is the most interesting and useful type of one, and beta is omega root LC is another interesting aspect. That means if beta is omega root LC or the linear function of the frequency, then only the velocity is becoming simply a constant. So this is a very useful one, and most of the times in your other subjects also, like filters and other things, whenever you design, you say we want a linear phase filter. That means from input to the output, when the signal travels, the phase shift that is going to be there, that the beta factor for the signals, we want it to be a function of frequency all the time. Why linear phase filters are only used is from this point. That is, when their beta is proportional to omega root LC, then only the velocity is equal to 1 by root LC. When only the velocity is independent of frequency. All the frequency components of the signal travel with the same velocity. As they are traveling from input to the output, same length of line, and velocity is independent of frequency. So the time taken is same for all the frequency components. That means when you give the signal with various components of frequencies, then all of them travel through the same circuit or the network for the same length with the same velocity. So they arrive at the output at the same time. So when they are recombined, the original signal is same as the signal given at the input side. So there is no distortion for the signals. So for the signals not to have any distortion, or for the signals to arrive at the output at the same time, okay, then this is an important parameter. Beta must be linear function of frequency. That's why they are all known as linear phase filters. That means linear phase constant. That's the actual meaning behind that. It's a phase is not linear. Okay, phase must be same for all the frequency components. What is linear is phase shift constant or phase constant. Beta is omega times root LC. That is what one has to remember in this. Okay, so it's a very standard interview question we ask, that why do you need always linear phase filters? Because the filter, what we want is not to disturb the signal shape. Okay, filter has to do other things, but not the signal shape has to be distorted. So in that sense, beta, we want it to be omega root LC type of ones. Okay, and velocity should be independent of frequency. So all the frequency components travel with same velocity and arrive at the output after equal distance at the same time. So when they are recombined, the signal shape is maintained. Okay, so velocity is equal to 1 by root LC. And what happens to the characteristic impedance? So if you take the characteristic impedance from RLGC values, square root of R plus j omega L by G plus j omega C, When R is equal to 0 and G is equal to 0, that is when you are considering a lossless line, then the square root of j omega L by j omega c is going to be simply root L by C. Again, Z naught is going to be a real value, root L by C. It doesn't have any imaginary component. X naught is going to be 0. R naught is equal to root L by C. So this is another favorable situation for us. So Z naught is real value and beta is a linear function of frequency are the resultants which give rise to a very favorable situation for the signals to travel. That's why in most of our day-to-day transmission lines we use, this is the condition we try to enforce. R naught is equal to root L by C. That is simply characteristic impedance is only a real value. That's what you will see in most of the transmission lines we use for our day-to-day activities to transfer the signals from your computer to mobiles or from a router to your laptops or mobiles you are using, sometimes some wired connections or even tabs, etc. Whatever USB connections we are all using to take a printout of your documents from the laptop to your printer, we use all these USB cables. All these things we try to enforce this situation. Beta is omega root LC, R naught is root L by C. That's why if you see any transmission line, if you ask the user what is the characteristic impedance of this line, he will say 50 ohms or 75 ohms or 300 ohms like this. What does it mean? We are saying impedance, but simply saying 50 ohms or 100 ohms. Does it mean 50 plus J50 or 100 plus J100? No. It is 50 plus J0. That 0 is the most important. If there is any complex value into this, it indicates that it is a lossy transmission line and many other problems are associated with this. So to avoid all that, we try to always realize the lines in this manner. R equal to 0 and G equal to 0, we try to achieve it. In most of the practical cases, we try to get Z equal to 0 without much of a problem, but R is very small value what we are going to get. That's why your cable TV operator, though he is using a very good quality transmission line, but after certain distance like 1 kilometer or about 800 meters or so, he will put an amplifier for the signals. If you ask him why an amplifier is required or a booster is required, he will say the signal undergoes loss. Where from this loss comes? Because the R is not equal to 0, a very small value, then alpha is going to be present, indicating that the signal amplitude goes down. So if the signal amplitude goes down, the TV will not be able to recognize the signals properly. So to get the signal reception on the TV very good, the cable TV operator uses an amplifier at regular intervals to boost the signals to overcome the losses that are going to come. So if the loss of the signal is very high, he has to use more number of amplifiers. Using amplifiers is an expensive proposal. Plus, to boost the signals, an amplifier requires some source also. So he has to provide a power supply connection which consumes power on regular basis. So there will be an initial cost of amplifiers to purchase them, as well as a maintenance cost to provide the power supply to all these things. So if you consider a low quality cable for the signal transmission, the R value is going to be large for that. That's why good quality cables are preferred, so that R is very much close to 0 and you need not use good number of amplifiers, and regular power supply to all these things can be avoided. So that's how always we try to look at the loss factor of these transmission lines to purchase for long distance communications. Okay, so this is the importance of all this discussion whatever we have regarding the lossless lines. Okay, we are going to have some more things towards the end of these topics also. So please remember, for all our future discussions, we normally try to first consider that the line is a lossless line. Okay, so R is 0, G equal to 0 are the most favorable situations. Some more aspects of this we shall discuss later. Okay, to start with. Let us complete at this point. So let's come back to the problem where we have taken up earlier and see what are the other aspects of this. Okay, so the same problem I'm going to use. So Z0 we have calculated earlier, and let's go to the, sorry, 1 minute. We are going to take up another problem. Yes, this is the one. Let us try to work out now. Okay, so lossless transmission line is mentioned. Velocity of propagation is 2.5 into 10 power 8. Capacitance of the line is 30 picofarads per meter. Find the inductance, phase constant, and characteristic impedance. So what is given is V. What is also given is C, and it is mentioned that F is 100 megahertz. We want to calculate these details. So velocity, just now we have calculated, is equal to 1 by root LC. So C is given, velocity is given. We are asked to find L value. So L is equal to 1 by CV square. L is equal to 1 by CV square. So substituting the values given, C is 30 into 10 power minus 12 and V is 2.5 into 10 power 8. That square is to be taken in this case for this. So putting these values, we get L is equal to 533 nanohenries per meter. Okay, so that is the first one. What is the inductance per unit length per meter of this line? So that is calculated. Then phase constant is to be calculated at 100 megahertz. So phase constant is calculated from the basic equation. Velocity is equal to omega by beta. So omega is known, V is known. V is 2.5 into 10 power 8. Omega is for 100 megahertz, 2 pi into 100 megahertz. So beta is equal to omega by V. Omega is 2 pi into 100 into 10 power 6. Sorry, it is 100 power 6 mentioned. Unfortunately, it is 10 power 6 only, divided by 2.5 into 10 power 8. So when you work out this, you will get the answer as 2.51 radians per meter. So that's how the second bit is answered. Phase constant is calculated from the velocity and radian frequency of operation. V is equal to omega by beta is the equation by which we are going to work out this. Now, once we know L and C values, and we know that it's a transmission line which is lossless, so we can calculate the characteristic impedance now. So the Z0 is equal to root L by C. That's what we have just now seen the equation. So this L value, whatever we have calculated, 533 into 10 power minus 9, and C value is given, that is 30 into 10 power minus 12, and the square root, when you take the ratio of these two things, you get the characteristic impedance, which is only a real value, given as 133.29 ohms. Okay, so this is another numerical which is easily worked out from the given data. Is it okay? First, please check all these things. Okay, whatever is given is C is given, frequency of operation is given, and velocity is given. With these things, we are asked to find the L value, inductance per unit length, phase shift constant, beta, and Z0. Okay, so with these things, first L is calculated, taken as L is from velocity and capacitance values. V is equal to 1 by root LC. V is known, C is known. So L is calculated 1 by CV square, which is coming out as 533 nanohenries per meter. Then V is known and omega is known. Using V is equal to omega by beta, we calculate beta value. That is, beta is omega by V. So putting the values of omega and V into this, we get the value as 2.51 radians per meter. And once we know L and C, we can find out Z0, that is root L by C. So that is coming out as this 133.29 ohms. So this is a simple case, and these problems can be found from the website gradstack.com. Gradstack.com, you can just see, and there the electromagnetic field theory subject you can choose. Okay, and transmission line topic, solve problems, and you can work out many other problems from the subject whatever we have discussed so far, you can find out. There are similarly many more websites like sandfoundry.com and many others. So you can find out many numericals on the web and work out all of them from the given slides, and you can be very much comfortable with these things. Another one which is now is to be taken regarding these things is another problem. Let us try to work out before we close for the day. So that is this. Yes. Okay. So a 100-kilometer telephone line has a series resistance of 4 ohms per kilometer, an inductance of 3 millihenries per kilometer, a leakage conductance of 1 microsiemens per kilometer, and a shunt capacitance of 0.015 microfarads per kilometer. And the radian frequency of operation is 5000 radians per second. So at the sending end, the voltage is 100 volts peak, okay, and the series in series with the resistance of 300 ohms. The series resistance of the source is 300 ohms. The load at the receiving end is 200 ohms. So find the voltage and current as functions of Z, okay, and find the values at the midpoint of the line, and so on. So what is that midpoint at 50 kilometers? What are the voltage and current values? If the load current is this, that is what is to be decided. Okay, so please remember R, L, G and C are given not in terms of per meter, in terms of per kilometer they are given, and the length of the line is mentioned to us as 100 kilometers. So frequency of operation is given. So what are the things from this we can find out? So R, L, G and C are now converted in terms of per meter. Okay, so R prime, L prime, G prime and C prime are now units per meter, not per kilometer. Okay, and similarly omega is there. So voltage at the source is 100 volts and series resistance is 300, and the distance of the line is 1 into 10 power 5, 100 kilometers. So 1 into 10 power 5 meters. So what is the current at the load is also mentioned, and ZL is 300 ohms. Okay, the load value is 300 ohms. So what are the things? Z0 is calculated first. What is the impedance of this line? Secondary constant. So Z0 and then gamma values can be calculated. Okay. So once we have Z0 and gamma, you can find out what is the voltage on the transmission line. The voltage on the transmission line is represented as V0 plus e power minus gamma Z plus V0 minus e power plus gamma Z. What about the current? The current is V0 plus by Z0, because at every point voltage and current ratio should follow your Z0. So V0 plus by Z0 times e power minus gamma Z minus, why minus? Because V0 minus by I0 minus should give you minus Z0. So I0 minus by Z0 e power plus gamma Z. So substituting the information that is given, you can write these aspects, and V0 plus is ZL plus Z0 times IL by 2. So ZL plus Z0 is given and IL is also given to us. So V0 plus is calculated, and V0 minus is ZL minus Z0 times IL by 2. So that is how the V0 minus is also calculated. So once we know V0 plus and V0 minus, we can write the equations for them. And now what we are interested is at Z is equal to L by 2, that is at 50 kilometers, what is the voltage and current we are interested to find. So substituting these values for Z is equal to 50 kilometers, we get the voltage expression in this manner and the current expression in this manner. Okay, so this is the way a voltage and current at any location can be calculated on the transmission line from the given values of R, L, G and C, as well as the source current and source resistance and other values. Okay, so with this, let us try to complete. What we have studied today is how to find the voltage and current expressions on the transmission line with distance variation. Okay, the distance variation is going to give various values of voltage and current. So what are the expressions for them is what we have discussed. And also we come across the secondary constants gamma and Z naught. Okay, gamma is per meter and Z naught is ohms. Those are the units for these two cases. Okay, so with this we have also worked out some two simple problems regarding the voltage and current to be found on the transmission line, and also other parameters like velocity of propagation and the phase shift constant and other aspects also we have calculated today. And in the coming class we are going to go further in these things regarding the other types of transmission lines and how to calculate the impedance at any given location if the line is terminated with an impedance other than the characteristic impedance. And with that, if the line is terminated with characteristic impedance, what advantages we are going to get, we shall see in the coming class on Friday. Thank you for the patient for listening. Okay, that's the end of the class today.